Hello everyone, welcome to lecture 7. In this lecture, we're gonna continue talking about the contents in chapter 8. So we'll cover the section 8.4 to 8.8. And the first topic is the stress anisotropy and the inherent anisotropy. So stress anisotropy is the anisotropy in soil because of the different stresses in planes. So you may have the vertical stress bigger than the horizontal stress, then this will occur. This will cause the stress anisotropy. And inherent anisotropy means that the fabric, because of the fabric anisotropy in different directions, it causes the different permeability or properties in with respect to each direction. So for example, if you have a soil that's like very platy one and it's piled up like this, then the permeability in this direction, KV, will be different from KH. And even though all the stresses are isotropic, so the stresses are all the same in every direction, the property can be different depending on the direction because of this inherent anisotropy. So stress anisotropy and the inherent anisotropy, those are the basic and two fundamental mechanisms causing the anisotropy in soil and rocks. So P-wave motion, P-wave particle motion is parallel to the direction of the wave propagation, and S-wave is perpendicular to the direction of the wave propagation. And in both ways, P-wave, when we talk about the particle motion and the wave propagation direction, because the particles are moving in direction, and also wave propagates in the same direction, right? So then it only counts the x direction. So this is the x direction stress. But in the case of the shear wave, it's a little bit complicated because the particle motion can be in one plane, but the wave propagates perpendicular to that, right? So then there are two planes that are involved, x plane and y plane. So sigma x and sigma y are involved in this equation. And then these are the equation. So let me write it down. And maybe sigma x is the stress in the perpendicular, the parallel to the wave propagation direction, and sigma y prime is the stress parallel to the particle motion direction. Okay? And then if we manipulate these two equations, then we can have this one. This is the mean effective stress, or the mean stress, and this one is deviator stress. Just like we define the stress in the triaxial condition. So in triaxial condition, there is a sigma c, and there's a deviator stress, right? And deviator stress is sigma 1 minus sigma 3, and the isotropic stress is the sigma 3, right? And sigma p prime is sigma 1 plus sigma 3 over 2. Right? So then here the sigma p is the mean stress, and the sigma d is the deviator stress. And sometimes you have you divide by 2 or nada. So here that they use the sigma x plus sigma y over 2 as the mean effective stress, and sigma x minus sigma y over 2 as a deviator stress. Deviatoric stress or deviator stress. So then, how does the wave velocity changes with the stress anisotropy? So let's look at this figure, and this is the result from one paper by Casagrande and Santa Marina, and this is the start. Here. So there's an isotropic loading. So initially, the specimen was loaded by sigma naught uniformly, so it increases like this, and then from here, so this was the marked at the square, and square is here, right? Then what happened? They have axial compression loading, so they applied additional stress here, the axial stress, and with the axial stress from this point up to this point, so the vertical strain is induced by about 1.4%. Okay. After that, this is removed, so the unloading goes down, and when the all the deviator stress is gone, then I think this is the same level, right? So then isotropic unloading, so sigma naught is removed. Okay, and then when they measure the permeable, the wave velocity, shear wave velocity, and the damping ratio in the I think the resonant column, so they use the resonant column here, RC. Velocity increases and decreases during isotropic loading. So IL is the isotropic loading, and IU is the isotropic unloading, right? So it was just a unique line, and this wave velocity can be defined as sigma naught beta times alpha, right? And the damping ratio also collapsed into one trend. And what about the wave velocity in this region during this deviatoric stress increase and decrease? And when they plot it, it's off from the trend. So this line is a isotropic and isotropic loading and unloading line, right? And you can see that it has a different slope, so that it's off from the trend. So isotropic loading will have its own velocity trend, but as soon as you're introducing the anisotropy, the stress-induced anisotropy, then the velocity trend will deviate. And this is another experiment, and you can see that firstly it was isotropy loading. Right? So they apply the sigma naught, right? Sigma naught increased, and then IEL is the axial extension load. What they did is that they decreased the vertical stress only. So they removed this part. So minus delta sigma D. So that means that the sigma naught, the axial load is smaller than the lateral load. So lateral stress is bigger in this region, right? Sigma H is bigger than the vertical stress. And then, so they are removing the vertical stress only to a certain point, to this point, and then they add it again to become the isotropic, and then unloaded the isotropic stress, decrease the isotropic stress as a last stage. So then when we plot the wave velocity for this region, right, and this region only, then you get this data. Again, it's deviate from the isotropy loading curve. And the damping ratio is the same. Damping ratio also deviates from the isotropy loading. Okay, interesting part is that this one, the damping ratio decreases as the confining stress increases, right? Isotropy loading increases. And here it's almost the same. It kind of decreases, right? Or it increases actually, right? As the confining stress decreases. So damping ratio increases. And also it follows the different shape. Yep. So then how do we use this kind of a wave velocity characteristic, the wave velocity and the damping ratio characteristic, to describe or to predict the stress condition? So then we can do some analysis using this equation and this equation that we saw in the previous slide. So when we plot the theta, which is the exponent, the power exponent, indicating the sensitivity to the x direction stress increase, and delta is the y direction stress increase, the sensitivity value. And you can see the theta and the delta is about like 0.1, 0.16 and 0.17, right? But when you split into mean effective stress and deviator stress, right? Deviator stress, then you get this eta and psi, right? And eta is about 0.28 and the psi is 0, right? Very, very interesting. So for the isotropy loading, when you sum this one, 0.12 plus 0.16, it becomes 0.28. So it becomes the same with this mean effective stress power exponent. Same with eta. And strong effect, isotropy loading has a strong effect on the velocity in particle motion than in the wave propagation. And velocity is determined by the mean stress in the polarization plane, not the deviator stress. Or I can say deviator stress. Right? So anisotropy loading causes anisotropy in the polar distribution of contact forces and in the distribution of contact. And it's called the stress-induced fabric anisotropy. And inherent anisotropy is the distribution of the interparticle contact that developed during formation and preferential particle alignment of the plate particle or eccentric particle. It's like if you have a rice, and then when you shake it, and it will deposit like this with the preferential alignment, and then this will cause the fabric anisotropy, and it's called inherent anisotropy. Okay, so then I think it's again the wave propagation is sigma p prime, which was before sigma x plus sigma y over 2, and yeah, so this is the same. And sigma m prime, sigma p prime is the stress in the direction of the wave propagation, and sigma m is apply the stress along the parallel to the particle motion. So VHH is that the wave propagates horizontally and also the particle moves horizontally. And VHV means that for the S wave, wave propagate horizontally and the particle moves vertically. And also there can be a different angle, right? Except for the vertical and the horizontal. So wave can also propagate at a certain distance, a certain angle, right? Kind of diagonally, but the particle can move horizontally. So then it's gonna be VH theta. Or it could be different way, V theta H. Okay, stress-induced isotropy. This is a very interesting experiment with the band element, and band element is like this kind of plate, and that shake like this with the cantilever beam shape, and at the one end is fixed and the other end is free. So when you apply some volt here, then it moves like up and down. So then it propagates shear wave. And it's like a plate. So then you can have this one like in this direction and vertically aligned. And in between, you can also adjust the angle of the plane. And this will determine the particle motion angle. So here, the propagation direction is horizontal. So VSH. VSHV, VSHH. And sigma 3 here is the direction of the wave propagation, so it's horizontally, and sigma 3 is the horizontal stress. And sigma 1 is the vertical. So then, when you look at the result, sigma HV is about here 90, around like 90, more than 90 meter per second. It's a little less than 90 meter per second. So the velocity changes with its angle or the plane of the particle motion, even though the wave propagation direction is the same in the sigma 3 direction. Particle motion changes from sigma 1 direction to the sigma 3 direction. So then, in this case, the particle motion, the stress that the particle is feeling, the vertical stress. Let me go this one. So when this one propagates, the wave oscillates, the make a particle motion moving up and down, and this one, the particle moves horizontally. So this particle will be more governed by the sigma 3, but here this particle will more be subjected to sigma 1, right? So when you move up and down, you're feeling the vertical stress better. When you move like horizontally, then it's gonna feel the sigma 3 more efficiently, more effectively. So then because the sigma 1 is bigger than the sigma 3, right, here, this wave velocity will be bigger than this wave velocity, right? And this result kind of proves the concept of this particle motion stress and propagation direction stress. Sigma P and sigma 1. Again, the different one is it's about the inherent on isotropy here. And if you imagine a kind of clay particle that's platy, or you can imagine a rice. So it could be a rice grain, long rice grain. And then one shear wave propagates this direction, but it polarized vertically. So by the way, the stresses are isotropic. So sigma 1 is the same with the sigma 3. And in the other case, wave propagates vertically, so this direction, and it moves, the particle moves this direction. And when you compare the wave velocity, which one will be faster? The result shows that this one is faster. Yeah? You can see that it can go up to 200 meters per second, right? And this one is only like 150 meters per second, right? It's a little bit tricky, and here it's a little bit less, right? It's just less, but when you look at the unloading part, it's almost the same in the low stress regime, but in the high stress regime, this one is bigger. And then we can kind of say that the Vs is higher when the main axis of the particle is parallel to the propagation direction. So as the wave propagates this direction, it's faster than it's going to the this direction. Why is it? The reason I think is that you have less contact through the media to a certain distance. So, for example, going to one, maybe like, let's say that this is the same 10 centimeter, okay? 10 centimeter from here to here, and wave experience one contact, 2, 3, 4, maybe 5 contact, right? But for the same amount of the 10 centimeter, it's gonna feel 1, 2, 3, 4, 5, 6, 7, 8, maybe like more than 10 contact. So then, because if you have a more contact, it means that the grain contact will have to transfer the energy to deliver the oscillation energy, and that's the wave propagation. So then this number of contact and contact will degrade the wave propagation, kind of slows down. So one of the explanation is that because you have a less discontinuity here, and this way is faster. And to get the certain distance, you are experiencing more like solid parts. So favorable anisotropy is there, and this can be applied to the clay particle. Okay, so next section is about strain effect. What happens if your excitation level is above the linear threshold strain? So linear threshold strain is a little bit difficult to define, but you can think of this way. So if you have two grains like this, and how much this particle can move to this direction, and then it can come back without falling down, right? Maybe like this much. So then this is the shear strain that can be recovered. Or if you can go more than that, so if you can move like this much, and this will be the strain, shear strain, that these two particles can recover its original position. And that's the concept of the linear stress threshold strain. If the strain is bigger than this threshold strain, then it will cause some permanent deformation. It's called a plastic deformation. So as you have a plastic deformation in soil, soil gets softened. Okay? Not the hardening effect. So then what happens? Stiffness goes down. So as the shear strain increases, it was here, right? Before it's the resonant frequency, but anyway, so I think it's proportional to the Gmax. The stiffness, the higher resonant frequency is a stiffer material. So then it kind of degrades with an increase in shear stress. And it's all same trend for the different level of confining stress. So this shows the same. Its velocity. Shear velocity is constant for a certain, to the certain strain, which is the elastic threshold strain. And after that, it degrades. So it kind of decreases. And for the same here around damping ratio increases as the shear strain increases. So then when you describe this kind of experimental trend with some mathematics, you can use the hyperbolic model. So this will allow you to get the d-mean. And the hyperbolic model itself, it starts with 0 when the shear strain is very small. So it's going to add up to get the the damping ratio increase by this much. So this is by d height, and this is by d mean. And there's some questions how the effective stress or the effective confinement affects the d mean. Right? Is the d mean is function of sigma naught prime? In some cases, in some experiments, say that the effective stress doesn't have influence on the damping ratio, but some studies says that it has. So as the confining stress increases, you have a lower minimum damping. But it's kind of controversial still. So this table shows the hyperbolic model and the Rambo-Osman model for the shear stiffness degradation and the damping ratio. And the next topic is the effect of the contact level forces. This table or this figure shows the relativity between the forces as your particle size decreases. So when the particle size is big enough, like here it's 10 centimeter, and this is 1 centimeter, and this is 1 millimeter, right? And this is 1 micrometer. Right? When the particle is like bigger than 1 millimeter, skeletal force governs its behavior. So gravitational force due to the weight of the particles. So when you think about the gravels and sand, that's what happens. So then skeletal force is too big for the comparing to the other the capillary force and the elliptical force. So in here, if it's gravel, then capillarity will be relatively small. Huh? So the suction, you don't need to consider the suction for the gravelly soil. But capillary force becomes important as the particle size decreases. And for example, like this is the capillarity. Yeah. And when the particle size is about like 10 micrometer, it's about the clay size, right? And your region of the interest, the depth of the interest is about like up to maybe several 1 meter. Then your capillary force will be much bigger than the skeletal force. So then capillary force becomes important. Then there is the dominant factors governing the mechanical behavior. Or if the overburden stress is small, so there's not much the effective confining stress, and you're looking at very like shallow depths, then the clay double layer like repulsion and attraction becomes the significant portion determining the mechanical behavior. Okay, so intersection with the thick line, okay, yeah. So this kind of shows that how the contact level forces changes, the governing contact level force changes with respect to its grain size. Yeah, you can read this explanation. And then let's think about the kaolinite. And this is the self-consolidation test. So you have a suspension in the long column, like very high void ratio, the void ratio bigger than 50, and you shake it and just let it sit and let it settle down. So then I think the porosity in the beginning is almost 1, so it starts from here, and as time goes by it's gonna settle down, so it will be here and here and here and here, right? So then the porosity decreases here with time, and at the same time the shear wave velocity increases. So shear wave velocity increases and as the porosity decreases. And this shear wave velocity, initial part is about like 1 meter per second, very slow. But after the self-wave consolidation, becomes the wave velocity bigger than like 100 meter per second. And then after the consolidation, what we can do is that so here the loading has been applied to 100 kilopascal, so it's normally consolidated to this part. So now the wave velocity is about 50 meter per second, and it's a kaolinite. And what we did is that you have the band element at the top and bottom, and this is the clay, right? The water there. What you can do is you can add some salt. So you're just sprinkling the salt at the top, and what will happen? So it's gonna dissolve in this water, and it will go into and diffuse into the clay, right? So that's what this means. The case here, they used the potassium chloride, and the potassium chloride diffused into the clay pore water, and that increased the shear wave velocity this much. Why? Because as the ionic concentration increases, double layer thickness decreases, so that void ratio decreases, so that the shear stiffness increases. Oh, this was the bentonite, sorry about that. So pore fluid exchange it for a high concentration of the KCl, and the velocity almost doubles during the diffusion process. And as ion concentration increases, W decreases. Okay, next topic, the cementation, anti-cementation. This is also very interesting topic. I like this topic. Cementation and decementation occurs everywhere in nature, and you get a lot of precipitation of the ions, or also you can observe the diagenesis, turning the sand grain into rocks, and formation of the salts and calcite and different minerals. And artificially, you can add the cement milk, Portland like milk grout, asphalt, other type of the bonding agent to the soil to increase the strength as a soil improvement method. Stiffness response will change due to the cementation and decementation, right? And interesting part is that when the force is applied, here that you're creating the contact area like this, right? Contact deformation takes place, but as you add the more cementation, cementing agent, cementation creates the contact area so that it adds up. The contact area increases because of this cementing agent. Okay, for the uncemented soil, following this alpha and beta, the power law of the shear velocity, as the confining stress increases, shear velocity increases linearly, like as a straight line in a log plane, because of this power law. And here, this will be the beta. But if the soil, so for example here, when you apply the cementing agent, for example, we are adding cement milk, right? Or it could be you can add some epoxy, and then wave velocity will go up, right? And because it's very solid, it won't respond to any stress increment, right? So the shear velocity will stay constant even though you're increasing the confining stress, right? So it's called the cementation controlled regime. But if the stress is too high so that it can break the cementation or cementing agent, then now that the stress will take over also, and stress will determine the shear velocity. So it's gonna follow this uncemented Vs sigma trend when the stress is big enough to break the cementing agent. So that's what you see in this figure. Stiffness increases with increasing cement content. So this is a cement content. And beta is almost zero in this low stress regime. But as the stress increases, then now it collapses to the this uncemented line, and it becomes the stress dominant region. This is the real experiment. Here, to a certain point, here, this is the confinement. And after the confinement, they apply they injected the cement grout. So this up to this is the confinement. And at this 70 kilopascal, they injected cement. So now it increases to a certain value, to 500 meter per second, or 500 to 600 meter per second, from 200. RC test shows the same. So with time, as soon as you inject out some cementing agent, it increases shear velocity and also increases the damping ratio. Interesting to see that even though you're getting the stiffer material, the stiffness increases significantly, but resonance frequency also increases, but the damping ratio increases at the same time. We see this a lot in the frozen soil too. So when it's melted, damping ratio is low, and when it's frozen, damping ratio becomes high. So there are something to do with this solidification. Right? Anyway, if the frequency is taken into consideration, losses seem to remain fairly constant during the cement hydration and the hardening. Because the frequency is also increasing here. And what about the decementation? Decementation means that the cementing agent breaks by tensile or some compression because of the stress. For example, here you have an increase in stress before applying the cementation to a certain point, and then you apply the cementation. So now the stress is quite big. It was about how much? 400, yeah, 300 kilopascal, and then they added the cement here, and so it increases, right? And then they unloaded it, so it decreases to 70 kilopascal. That's what happens here. Huh? So then what happened? Okay, let's look at this one. So you apply the stress to a certain point, like 400 kilopascal to here, without treating anything. And then you apply the cementing, injected the cementing grout, so that it went to this high, 600 meter per second, right? And then you unloaded it. So now the soils are very compressed, right? Here, because of like 400 kilopascal. And then it's gonna be coated by this cementing mortar. Huh? And as you removing this stress, it will try to pop up because of the they were compressed and they want to extend, right? So then as they extend, it decreases to this point. And what happens? Because now that it has expanded too much, the cementation broken or damaged. It could be partly or completely. Right? If it was completely, I think it would go down this much, but it was maybe partly. From this point, I think it broken. So then when you load it again, it didn't follow the original curve here. Didn't follow that. It followed this direction. So up to 400 kilopascal, still it's damaged. The cementation is damaged by this much. And this is called a decementation. And this can happen during the sampling of your soil in the field, because if you think about the sampling, the sample using thin wall tube or undisturbed sampler at maybe like 20 meter deep, the confining stress could be 200 kilopascal, and when you sample it, you're releasing all the stress, so the confining stress becomes zero. And then, because of this release of the confining stress, it will try to expand. So then if there's like gypsum or calcite cementing the grains, it will be damaged. So decementation effect can be severe in the sampling. This is a different, okay, yeah, it's the same. So when you have a diagenically stiffened clay, so that means that the clay is kind of overly consolidated or overly cemented with some chemicals at low water content, so it's not fully saturated. Then you sampled out and you bring it to the lab, and it was like SY velocity was like what, 250. And when you add water, as soon as you're adding the water to that sample, they're absorbing the water and it becomes softened, so they collapses like this. So low S is the water filtration, the loss in skeletal stiffness occurs during the water infiltration. And yep, so this is another also example of the decementation. Here uncemented one, it shows go up and down like this, and go up and down like this. And when you have this soil, this is uncemented, and then cementation takes place here, so that it goes up, and when you keep increasing the stress, kind of goes like down here. So then what happens? Here the decementation, right? And then when you unload it, so also it decementation occurs. If it's not cemented, if the decementation didn't occur, it should be flat like this, right? Should be independent from the stress, but it's going down. That means that the stress is being released, so that the decementation occurs and the cementing agents are starting to break. Yep. And the last one is the Crypt, and Crypt is the deformation during constant loading condition. So when you think about oidometric test, this is the clay. You apply maybe like 100 kilopascal, right? And all the excess pore pressure is gone, so the delta UEX is 0. And if you let it sit for like several months, then still it's gonna go down, but it will, some deformation will occur, and it's called a Crypt or secondary consolidation. So the stress conditions are all the same, but the deformation occurs with time. So Crypt is time-dependent deformation. So the strain rate is defined as a function of the stress state and the time. So here the M1 is the parameter sensitive to the stress increment, and M2 is about the time dependent parameters. So if we do the Crypt study, so here what they did is that they used the lead shot. It's made of lead. 납구슬. Lead shot is very soft, so it will be softened with time. So when you increase the stress, for example here, so from to here, when you increase the stress, it was here. And after 100 hours later, it will go up by this. So what's happening? So it was before, it was like this, but in here, if I can exaggerate, like this, after 100 hours. So that the contact area becomes bigger, so that the velocity goes up by some amount. Also the damping ratio also goes down, so energy dissipation is smaller. So observation here, the Vs remain almost constant during the unloading. The contact size determines the stiffness, but the shear velocity increases significantly with time at each loading stage. Attenuation decreases with time at each loading stage. This means that the prevailing loss mechanism is stress dependent. Still, it's the same with the lead shot experiment, and if we plot it against the vertical strain, not the confinement, then you can see that it follows the one trend line. And for the damping also, it kind of follows almost the same one trend line.